All right. I hope this is also audible right at the back as well. And it's great to see the hall completely filled in right now. We will start our day with the first keynote speaker. We have Shakthi here, who is a free and Libre open source software developer who's been actively working with the community, industry, and the government for more than 2 decades. Well, that has something to say. And he has organized numerous workshops, and given technical talks at various colleges, universities across India and even abroad. Shakti also holds a master's degree in information technology from Rochester Institute of Technology from New York, US. Well, let's give a quick round of applause for Shakti and start with our first keynote.
Can you hear me at the back? All good? All right. Very good morning and welcome again to PyCon India 2025. So the previous talks that I've given at Nimhans have usually been in the afternoon. And I asked the organizers, they usually tell me, or give me an excuse saying that it's very hard to sleep in your talk. And so it's very easy for us to schedule your talks in the afternoon. The first time I'm doing a talk in the morning and the first talk of a conference. So with that, let's get started on today's keynote. I'll make this presentation available. I don't have a lot of slides. I do have some demos, but I do have a few key takeaways that I would like you to take from this session. So let's get started. So brief introduction. Yeah, I've been a free software enthusiast for a long time. Most people know me because of this book that I wrote a while back. It's funnily titled, but most students who are familiar with the Google Summer of Code, KDE, Mozilla projects actually use that to do their work. I've also launched a new course based on that book, and I've been in the community circles for a long time. Mostly been working out of deep tech R&D companies out of universities in India and abroad. And of course, my online presence goes by the name of Shaktiman, which people are familiar with. So today I'm going to talk about nuclear engineering, physics, and some of the challenges that have come up recently. And to start with, nuclear fission has been there for about 60 years, as you already know. And if you go back to your high school physics, we know that if you have a neutron that bombards with the uranium, and you get these krypton and other neutrons that are produced, which also generate energy out of this equation. And that is the Chicago Pile 1 building, which is part of the metallurgical engineering department at the University of Chicago. It's currently under the Regenstein Library. It's decommissioned right now, but that's where Enrico Fermi actually began the experiments. And later on, of course, Oppenheimer came, and the Manhattan Project actually started there. Fusion has a little bit a late history. It began a bit later out of the Princeton Plasma Physics Laboratory. And then over years, there have been multiple designs that people have come up with. And there was regulation, there was JET work that came up. There were tokamak designs, which we'll go through today. And there were few prototypes that have come out from Japan and the US. Okay, so related to fission, the fusion industry has been a little bit late, but there's more regulation in the nuclear fission companies, right? Nuclear fusion as such, of course, you have a similar concept. You bombard two particles, and then you generate a bigger particle, right? Sometimes you could have like deuterium, tritium, which have a smaller nuclei, but you have like millions of electrovolts of energy being generated. Nuclear fusion actually is quite safe and clean energy. There are different techniques that people have over the years tried to build fusion reactors. So there's gravity-based, magnetic-based, inertia-based confinement models. Stellarator and tokamak are similar. They are different designs physically. Of course, some universities like the University of Wisconsin-Madison have like magnetic mirror designs and so on. So I just listed a few examples here that people have been exploring nuclear fusion in the past. Why is it exciting right now? Because you see the Department of Energy in the US is sort of allocated about $8 billion in investing in alternate energy sources. And they're quite interested in seeing how fusion can be useful to support our energy needs. And MIT has been working a lot in this field over the past, and Lawrence Livermore National Laboratory as well. They have some of the biggest supercomputers where they can actually run some of the physics simulations. And the other news channels like BBC have also reported that we will expecting some nuclear fusion plants being deployed in the coming years. So the exciting times right now, and this is the French who have been able to run a tokamak design nuclear fusion plant in France. It ran for about 22 minutes. And so they've been able to maintain that and generate some power out of the reaction. They are trying to push that to about an hour. And there are challenges, as we will see. The main thing is the temperature. So this is what you see inside the fusion reactor. This is the camera, and then you actually have the plasma flowing through the reactor. This is the proposed plan in southern France. It's called International Thermonuclear Experimental Reactor, ITER. It's already being built, and it's costing about 22 billion euros. And India is also a key partner in this project. And again, they have at the core they have this tokamak design, which we'll go through next, and then they have all this monitoring and other support systems around the whole plant. It's a huge project, and it's currently being built in the southern of France, somewhere near Nice. Now, let's look a bit of what the tokamak design actually looks like. So this is basically called a toroidal design. So if you see here, we have at the core, this is a plasma that flows across, right? And then you have, this is the core, the toroidal one, and then around it, we have the magnetic fields, which is called the poloidal. So you have, it's like a donut-shaped one. So toroidal is the donut shape, and then the poloidal magnet is there to sort of maintain the plasma confinement inside the fusion reactor. That's a very simple design, and the plasma shape will affect the stability. So if you look inside the core of the reactor, the temperature goes to about 150 million degrees Celsius, which is much hotter than the core of the sun. So how are you going to maintain the stability, right? How are you going to maintain the particles, the neutron bombardment inside the reactor? And there are a lot of challenges there, but this is one of the examples of a nuclear fusion reactor that the Japanese once implemented, and then, of course, now the French have it, and there are some more companies who are starting to work on this. So, with all these challenges in the fusion space, and you ask the scientific community, how can we actually help speed up the development of these fusion reactors? Are there any solutions that we can help analyze and make it more safer, more productive, more faster? And of course, when you talk about the scientific community, there's no bigger than the Python community itself. And so there are many free and open source software tools available to be able to model these fusion reactors. And one example here is the OpenMC, open source Monte Carlo simulation project, which came out from MIT. There's Dr. Paul Romano, who's currently at the Argonne National Laboratory, who is the lead maintainer for this project. And the entire code is actually available on GitHub. He specializes primarily on neutronics, and then he works closely with the computational reactor physics group at MIT. It is primarily written in Python. There is some C++ code for the simulation, and it's released under the MIT X license. It also has hybrid MPI and OpenMP programming model support. So if you want to simulate it for say 10,000 particles, and you have say hundreds of iterations that you want to run across huge supercomputers, it is still possible. I'll give a quick demo here on this workstation laptop at a smaller scale, But these are traditionally run on these HPC systems for getting more precision analysis. There are different aspects of these reactor models that people are interested in. Some are interested in the heat. How can you actually control the heat? And how do you model that in Python? Some are interested in neutron transport. Some are interested in material design. Right? There's not a lot of data available right now. There's still a lot of research going on to see what materials we can use in building these models. And some of these codes are actually available online. There's one specific pull request that I want to highlight here, which is from Jose, who actually says there's an error in the scattering data in the thermal elastic cross-section. And so he says this is not itself an OpenMC bug, but it's more likely proof that the thermal scattering evaluators are horrible, horrible people in trying to change academic results into real practical value, right? So this is PR3233, and he actually shows the results of what the cross-section temperature error is, and he actually has a Python fix to be able to do the proper heat, temperature, reflection in the model, right? And this is something I really want to see a lot more in the Python community. I know in the AI ML space, there's a lot of research papers and people do a lot of reviews and they cite research publications. But whatever Python project that you're working with, what I would like to see is more reference to academic literature. Make sure you have a well-detailed pull request that you make. Right? I'll show you that PR as well. Let me switch. Okay, so this is the pull request. I don't know if you can see from the back row here. I can try to zoom in a bit. So this is a specific pull request. I'm running BTOP here. So this is a 32-core machine. I have 64 GB, so I can show you some simulations. You can run it on the cloud, or you can run it on those HPCs. Okay, and here he describes the discussion there. He describes the actual formula that is actually needed from academic literature. There's a tool called Enjoy where they actually have not corrected it. So he says, let's fix it in Python. Let's do it the right way. Okay, so he actually explains the results, how he got the actual value, and there is this pull request here, of course. So these ENDF6 files that you see here, the ones in the ENDF6, they're all data files. So generally in some of these modelings, what we use is hierarchical data format files, HDF5 files, they use to describe the different models. And so here's some equations, and then, of course, Paul Romano comments on it. There's a PR, they fix it. So this is something that I would like to see a lot more coming out of the Python community here. Now, what I'm going to do next is quickly go through the tokamak design tutorial here. So this setup you can do on your laptop. It's actually using the Conda environment, which you'll be familiar with. There's also ways you can set up these Python packages without Conda as well. So it's up to you how you want to do it. I actually ran this simulation last night, so I'm just going to quickly walk you through the gist of what people do. So nuclear physicists, when they want to analyze, there are two types of people. Right? One are the generalists who want to quickly assess the big picture of things. And then the specifics like heat transfer, electromagnetic flux, and those things that they want to analyze. And so they come up with these kind of Python notebooks that they actually want to run the simulation to see how it performs. Of course, the OpenMC, there's a package you can just import OpenMC, and here they use matplotlib. The way they do is they start with a one-dimensional analysis, then they switch to two-dimensional, then they switch to three-dimensional. That's the way the thought process actually works, and that's how they do the modeling here. So in this tutorial, they basically import OpenMC library, the URL request, and they actually load the material information, whichever material that you want to model in your reactor. And then they have the high-level geometry of the reactor that you want to model, right? And then they plug in the material information, the characteristics or the properties into the geometry, okay? There are a lot of codes available for some of these metrics. And then they use OpenMC to do the cross-section. This is the cross-section on the cylinder from the top, right? And then you add the neutron transport. So now you inject neutrons into it, and you see how it actually reacts. And so the OpenMC simulation runs. This is the command line output. You can define the number of iterations that you want to run, and then at the end of the iteration, it basically provides the relevant heat, collision, statistics, and so on. This is at the high level, right? Now, let's take it very, very specific to the tokamak design. Same concept. Here they use the 3D modeling from John Schimmel's package called Paramac. That's completely Python and open source. It helps you to quickly develop 3D nuclear fusion reactor models. So you can just import it straight away if you want to test that. And then you add the materials that you want. So here we have multiple coils, right? So you have the magnetic coils. So you add all those specific material and its attributes. And then, yeah, you want to create the distribution of particles that you want to use. Generally, they test here with like 20 million electron volts for the simulation. And you can change this. It's quite convenient here. And then you plug in the materials into the geometry. You define the fuel sources. And then you actually run. This is a cross-section of the 2D here, right? So you have the tokamak, you have the core. The violet one is the plasma that you see, and then you have the coils at the outer, right? And there are some flux components in the outer, which we will examine. This is the cross-section. You can do a 180-degree cross-section, or if you want to analyze, you can do a 90-degree cross-section. You can run the simulation again. So here, running 10 batch sets. Usually you do like 10,000 particles, 50 batch sets, and maybe 100,000 iterations. You keep running that. Some of these simulations run for maybe weeks on these clusters. And it could be like a 1,000-node cluster with, say, NVIDIA GPUs, for example. Right. So here we somehow see the magnetic flux in the outer region. Okay, if people want to like study those aspects, you can see how the actual color gradient varies based on the flux. Now the next step you can do is also examine it more in detail. Let's say I want to like do a fine grain analysis on the outer design. So here you can take like a cross section of it. This is the cross section of the entire plasma and the coil. And then you run the simulation again. So tally here is what they use for the 3D array representation. It combines the nuclides, the filters, and the scope of the actual model. Then we rerun the simulation, and you will be able to see a more finer picture of how the magnetic flux is on the boundary of the reactor. Right, so this is just one example of heat. There are a lot of examples in the OpenMC project that you can actually try out. Now, this is just one way of doing Monte Carlo simulation. But there are other tools like a Cardinal project, for example, where they do multidimensional physics. So it's not just the heat that you want to study, right? You want to understand the behavior between the magnets with the electric, with the plasma neutrons, with the heat, with the materials, and the reactor design. So it's multi-fidelity physics simulations, and that's where the complexity comes in, and that's where Python as a tool is really, really useful. Okay. With that, let me quickly jump to the other demo. This is the Cardinal. Let me quickly show you the Cardinal project. The one in Kalpakkam in Chennai is they're actually a breeder reactor. So it's actually a fission. They use uranium. Let me just open this GitHub. Moose is another framework that comes from Idaho National Laboratory, and they also use a framework for doing accelerated fusion and fission simulation. So here, if you have those, so fission also has a lot of requirements in terms of how you want to model it. So again, you have like a Python and C++ combination here. You have those multiple rods in the breeder reactor, how you can simulate some of these effects. There are quite a number of tutorials here. So again, this one you can use the Conda environment to set it up, or there's an instruction to set it up without it. I've actually used it without Conda here to show you how that's done. And you can get specific cross sections here to analyze the parameters that you want to visualize. There's another tool called Visit from University of California at Berkeley. They also have some good visualization for some of these computation outputs. Okay. So, yeah. So let me quickly jump to the, yeah. So here I have set up the tokamak design. I'm using about 22 CPUs on this VM. So I'll be able to run this. And for me, about 1,000 particles and 10 batch sets took about 6 to 8 hours on this machine. But again, depending on how much CPU and GPU you have, you can actually run this on your machines. And then this is basically output the actual geometry of the reactor, and it will also output the heat for each one of those simulation runs. And then you interpolate it, and you'll be able to see the whole three-dimensional aspect of how the reactor behaves at various starting conditions. Depending on the number of parameters there are, these things can become very complex, and that's why some of these physicists actually prefer to run it on these HPC clusters. Right. Okay, it is using all of those CPUs. So what we have here with OpenMC is called DAG-MC support, which is direct accelerated geometry Monte Carlo simulation. So they actually run the neutrons, they do the particle simulation, compute all the heat calculations, and then they generate the output results. And you can actually break this anytime, and then you will have partial results of the output files. You can still view it using Visit, for example, but then you really want to have like more finer grain and more detailed parameter values to be able to get a more accurate results. Yeah, this is the first batch. It'll finish. It'll do the finite element solver. They're usually using differential equations. And then again, it'll do the iterations for the second time and so on. Okay. Let me stop this one here, but do try to set it up on your system to see how this actually work. So actually, you see here the last row that the neutron transport, about 20 million electron volts, that's what they actually generate here in the simulation. So once I break this, there'll be some files here, like the solidout.e, solidout openmc.e, openmc0.e. Those are the files that you want to put in the visualization. And once you do that, you will actually see, go back to the presentation here. You will see the entire cross-section and the different heat values and the ranges, something like this here. This gives you a good picture of where you want to optimize and where you need to control more of the heat in the reactor. So this is just one example I've taken with the tokamak design, but there are like a lot of other designs that you can play around with. So what other challenges are there in the nuclear fusion space? Of course, the magnetic confinement is important because the magnets have to control the plasma stability inside, right? And they have to be stable. Do we have any stress modeling tools to be able to maintain that the magnets are able to withstand and the temperatures and also maintain the plasma flow? That's still an issue. High temperature requirements are still there. If you're able to sustain the reaction for a longer period, say days or months, are we able to sustain that for a long time? There's not a lot of data on material sciences, so can we actually work with the metallurgical department and find out if there can be more materials that we can actually use in modeling this with OpenMC. There is a lot of initial capital expenditure involved in this because setting up the plant, it takes billions of dollars of investment, and hence can we actually get more precise and accurate results using physics simulation model tools is something we should definitely invest in. It does take a long development time. Physicists, they're good in what they do. They may not necessarily have the software engineering experience. So having to work with them is important. Unlike fission, there is not a lot of radioactive waste in fusion. It's quite less. And the general public perception, right? People generally fear that, oh, nuclear reactors are dangerous, they might leak, and it will be hazardous for the environment. And those issues are still there. Of course, there are alternative energy sources that people have been investing over the years. There could be other competitors. There are also like political economic reasons. There is a lot of companies right now in the fusion space who are really, really pushing the technology and the physics into getting something out to be able to help produce that electricity that people need for the big masses. And magnets requirements as one way of actually implementing the reactor design. Intercelerator are other design models that people are looking at. So supply chain issues, those are things that people are facing and something that needs to be considered in the long run. But things are looking good. I think in the next few years, we will hopefully have more fusion plants producing enough energy to power the homes and industries. I would like to leave with this one quote from Oppenheimer, where he actually says that scientists should really be free to ask questions. And they should doubt everything. And if there is any errors, they should be able to correct. Very similar to what the pull request that we saw earlier, right? And we have to be pragmatic. At the same time, we have to make sure that we stick to the academic principles and discipline there, and we're able to follow that in whatever practical implementation that we do. So to me, the academics, the knowledge, and applying that in practice with Python is the key, I think, to be able to sustain long-term projects and also for a long-term clean nuclear fusion energy. So with that, I will end this talk here. I'm happy to take a few questions. Thank you.